Okay, here we're going to look at an introduction hypothesis test, or test of significance. A soda bottling machine is calibrated to dispense on average 20 ounces of soda to each bottle. We'll assume the amount dispensed follows a normal distribution, and a reasonable value for the population standard deviation may be sigma equals 0.2, okay, or 0.2 ounces. Okay, as consumers, we don't want the average amount dispensed to be less than 20 ounces per bottle, okay, because then we're going to feel like we're getting ripped off. Okay, so part A, how may you determine whether a machine is dispensing less than 20 ounces per bottle? Now, we don't know what the population mean is here, okay, but they're telling us that it's calibrated to dispense 20 ounces on average. So how do we know if that's true or not? Well, the idea here would be, just like in the previous topic with confidence intervals, you take a sample of size n, and then what are we going to do? Use that sample to make an estimate or prediction where we would expect mu to be. So what we look at is taking a sample of size n, and we'll find its sample mean. Then we apply the central limit theorem to construct a confidence interval for mu. Okay, so this is going to, hypothesis tests are going to tie in to the previous topics that we've done with the confidence intervals. Okay, so suppose we take a sample of 50 bottles and weigh them to get a sample mean of x bar equals 19.97. Now, I said you weighed them here, but this maybe a better would be like the actual volume to be 19.97 ounces. Don't get lost in that, though, whether it's the weight or the volume. Okay, x bar, 19.97 ounces. So we take a sample of 50 bottles, and we get a sample mean of 19.97 ounces. Okay, let's construct a 95% confidence interval for the population mean. Okay, there's nothing new here other than from the previous topic. A 95% confidence interval. We're going to take our sample mean, add or subtract our z star times sigma sub x bar. Well, in this example, our x bar was 19.97 ounces. Your z star value for a 95% confidence interval is 1.96, because the middle 95% of the data lies within 1.96 standard deviations of the mean. Okay, so that's your z star value. Sigma, we said, was 0.2, and we took a sample of size 50, so square root of 50. And then when you actually do those calculations, we end up with 19.97 plus or minus 0.0554. Okay, so that 0.0554 represents our margin of error. And our interval tells us that we are 95% confident that the true value of the population mean lies within our interval of 19.9146 to 20.0254 ounces. Okay, now comes the idea behind, okay, what is this actually telling us then? Well, we clearly see that 19.97 is less than 20. So our sample mean of 19.97, there is no disputing that that number is less than 20. But does your confidence interval support the claim that the machine is dispensing less than 20 ounces on average? Explain. Well, if we're 95% confident that mu is in our interval, isn't 20 in our interval? Okay, so that interval, that 95% confidence interval, does not support the claim that mu is less than 20, because 20 lies within our interval. So the sample mean could have been a little bit above 20. I'm sorry, the population mean could have been a little bit above 20 based on our interval that the sample mean of 19.97 gave us. Okay, so the idea here is, like the bigger idea, we didn't know what the population mean was. So we took a sample of 50 and it gave us a sample mean of 19.97. Because it was a sample, we're using that to estimate the population mean, and because it was a sample, we have to include that margin of error in there, because those 50 bottles, okay, were just 50 bottles out of probably millions of bottles that they have. So we have to introduce this margin of error, and we can't just say that, yeah, we know that 19.97 is less than 20, so obviously the population mean had to be less than 20. Okay, no, you can't say that, because that sample has some variation to it. Okay, and that variation has to do with the 0.2 and your sample size we took of 50. Okay, and that's where your margin of error comes from. Okay, so that confidence interval does not support the claim that mu is less than 20 because 20 is within this interval. Now, suppose we take another sample of size 50 and calculate the mean x bar to be 19.90 ounces. Okay, so we take a different sample of size 50 and we get x bar to be 19.90 ounces. Again, we clearly see here that 19.90 is less than 20. Okay, again, there's no disputing that. Let's construct a 95% confidence interval for the population mean. Okay, so we'll do the same idea again, another 95% confidence interval based on our new sample mean of 19.90. And then, does your interval support a claim the machine is dispensing less than 20 ounces on average? Okay, so if we do that, again, we start off the same idea, x bar plus or minus z star times sigma sub x bar. Substitute your values in. Now we have a sample mean of 19.90. Your z star is still 1.96. Your sigma was still 0.2. And you still had a sample size of 50. So what you might notice there is the margin of error does not change because we're still 95% confident. So nothing changed in the margin of error piece to get 0.0554. What changed was the center of our confidence interval was now 19.90, which is lower than what the first one was at 19.97. Okay, so this sample mean is farther to the left on the x bar distribution. So now when you actually do those calculations, you get 19.8446 and 19.9554. So here, we're 95% confident that our interval contains the true value of the population mean mu. Now notice that 20 is not in this interval. 20 is above this interval. So now, does your confidence interval support the claim the mean dispenses, or the machine is dispensing less than 20 ounces on average? Well, now we can say yes, because this 95% confidence interval supports the claim that mu is less than 20 because the entire interval of values lie below 20. So all the values here in this interval lie below 20, and we're 95% confident that mu is contained in this interval. Okay, so we can support that mu is less than 20 now. Okay, now really what happened here, okay, if we can see this okay, well, you take your x bar axes, and 20 is somewhere around these axes. Okay, so 20 is somewhere on the axes. When we did our first estimate, the first estimate for x bar was 19.97, and our interval was 19.91 to 20.02. So 20 was included in that interval. Now what we did in the second interval, we ended up with a lower x bar value, okay, of 19.90. So that sample mean was 19.90. And that interval spread from 19.84 to 19.95, which is below 20. So this is one of the intervals that does not contain the true value of mu, if the mean was really 20. Okay, so again, if we did this process 100 times, so we took 100 samples of size 50, we would expect 95 of them to end up like the first one did, the blue one here on my graph. Okay, the blue one, where 20 was included in the interval. And we'd expect about 5 of them to end up like the red one here, where 20 was outside of that interval. Okay, next example. We're going to look at that previous example using another method by determining the sample mean is whether the sample mean is unusual. Okay, and remember, as consumers, we're concerned that the machine dispenses less than 20 ounces. Okay, so now we're looking at. Oops, let me find my page here. If we're concerned that the machine is dispensing less than 20 ounces, what we're going to do is we're going to start by saying that we assume that the machine is calibrated correctly. Okay, so we're going to say, all right, company that's pouring the delicious soda into our bottles and making us fat and diabetic. Okay, remember, if we assume that it's calibrated correctly, then what assumption are we making about the population mean? Okay, so if the machine is calibrated correctly, aren't we assuming that it calibrated 20 ounces? Okay, so our assumption, and again, I already have these written down just to speed this up a little bit. Okay, these videos can get long, I know. Okay, the assumption we're making is that mu equals 20. The alternative to that assumption, well, there are a few different alternatives, but what we're concerned with is that the machine is dispensing less than 20 ounces. So how would you write less than 20 ounces? Well, you would say the alternative is that mu is less than 20 ounces. Okay, and the alternative is going to go along with kind of what we're concerned about or what we're claiming in the question. Now the company could be concerned that the machine dispenses more than 20 ounces. If that was the concern, then the alternative would have been that mu is greater than 20. Okay, so what our claim is on this one is less than 20 ounces, so we're claiming that mu is less than 20 ounces. Okay, so if the population mean really is mu equals 20 ounces, we're going to draw and label the sampling distribution of x bar for n equals 50, and we're going to use a sigma value of 0.2 again. So the population standard deviation is 0.2. Okay, so what we know about our sampling distribution of x bar, well, we know that the mean of the sample means is equal to the mean of the original distribution, which is 20, because that's the assumption that we're making, is that the machine was calibrated correctly, so we're assuming that mu equals 20 is a true statement. There, that's what we're going with. The standard deviation of x bar is sigma over square root of n, 0.2 over the square root of 50, which is approximately 0.0283. Okay, and here I'm using 0.0283 because 0.2 over square root of 50, it's hard to know like how big is that number. Okay, so the 0.0283 is a rounded value that we can use to label our axes. Okay, so when we make our distribution, by the central limit theorem, because n equals 50, that's a large enough sample size, the x bar distribution, or the SDSM, okay, remember this is the sampling the sampling distribution of sample means. The x bar distribution will be normal with the mean of 20 and the standard deviation of 0.0283. So when you label those values on here, okay, I know they get crunched up a little bit there. The center of the distribution is at 20, and then if you add and subtract 0.0283, 1, 2, 3 times from 20, you end up with these values across here. Now, what we're going to be interested in is looking at how far those data values are from the mean. So would an x bar of, say, 24 be unusual? Well, 24 will be well above 20, so that would have a z-score way out this way, okay, a very large z-score. If you had an x bar value of 20.0283, then the z-score would be exactly 1, which would not be an unusual value. A z-score of 2 would be 20.057 for an x bar value. If your x bar was 19.944, that'd be a z-score of -2 that corresponds to that. Okay, if you had an x bar value of, say, 19.5, 19.5 would be to the left of 19.9157, so that would be an unusual value way out here. Okay, so that's what we're going to be concerned with, is where do our values end up when you look at them in terms of z's. Okay, but we're going to get into that here in a minute. Okay, so once we have that distribution for the sampling distribution of sample means drawn, okay, so the x bar distribution, now we're going to look at our sample of 50 bottles whose sample mean was 19.97 ounces. Where is this value located in relation to our assumed value of mu equals 20? Well, 19.97, okay, we can see is just below 19.972. Okay, so it's going to be right around in here. Now we can see that that shouldn't be really an unusual value to get if the mean was really 20. An x bar of 19.97 is just under 1 standard deviation from the mean of 20. Okay, so let's calculate that z-score for x bar equals 19.97. So to calculate a z-score for x bar, okay, let me go back to a blank piece of paper for a minute. Okay, bear with me for a second. Okay, what we did before to find a z-score, okay, back when we started with the normal curve, what we did before was we said that z equals x minus mu over sigma. Well, now we're looking at, instead of x, okay, instead of random variable x, we have x bar. So now z is going to equal x bar minus, instead of the population mean, we have mu of x bar, or mu sub x bar, in the middle of our distribution. So we're going to subtract the mean of the sample means, divided by, instead of the standard deviation, now we have sigma sub x bar. So basically everything in your formula turns into x bars. Now, the way I kind of do that, like when I'm face to face with students, we'll start with x minus mu over sigma equals z, turn everything into x bars. Okay? So what we have here is x bar is 19.97 minus the mean of the sample means, which is 20, and then divided by, we're going to use the exact value of 0.2 over the square root of 50. We're not going to use the rounded value until we round the z-score at the very end. Okay, this rounded value, 0.0283, was just so we could put numbers on the axes. We're going to use 0.2 over square root of 50, though, for our exact value in our calculator. Okay, so when we do that, okay, we end up with a z-score of about negative 1.06. When you put the 0.2 over square root of 50 in your calculator, make sure it's in parentheses, okay, or else you're going to miss it. You get a z-score of negative 1.06. Okay, so that should make sense because 19.972 would have a z-score of negative 1. 19.944 would have a z-score of negative 2, and we can see we're between those two values. Okay, so that number should make sense. Okay, so is that value unusual? Okay, no, because only 1.06 standard deviations below its mean, or assumed mean, of mu equals 20. Okay, so a z-score of negative 1.06 is not far enough away from the mean to say that it's unusual. Okay, now we will get more formal into that, okay, in a few minutes or later on. But right now we're looking at 1.06 below, standard deviations below that mean is not too far away from the mean. Like if you're way out here, more than 3 standard deviations, or like over 2 standard deviations out here, okay, they may be far enough away from the mean to say, yeah, that's unusual for that to happen. Okay, so the basics here are saying if the mean really were 20, so the machine were calibrated correctly, we're assuming the mean was 20. 20 is right in the center of our distribution. So we wanted to test that. Taking a sample of size 50, we found their average to be 19.97 ounces. That is not far enough away from 20 to say that the 20 was an incorrect assumption. Okay, that's the essence of what we're saying here. Okay, so part D. What is the probability that x